GeoEstima Podcast, Season 2, Chapter 6. In the previous chapter, we talked about the three-dimensional geological model of a deposit, highlighting that it's a fundamental activity in the mining industry. Next, we will discuss the estimation of grades and other parameters in block models, continuing to explore and learn more about the geo-mining-metallurgical business in Chile and the world. Grade and parameter estimations in a deposit are carried out in block models, which are digitally representations of a mineral deposit or other geological feature, primarily used in the mining, resource estimation, and geology. The block model divides a deposit or area of interest into a 3D grid of blocks, where each block represents a specific portion of the volume and contains attributes describing its characteristics. Grade estimations are performed for each block using interpolation methods, mostly geostatistical, based on analyzed values from a limited set of samples primarily obtained from drill holes. The number of samples is significantly smaller than the number of blocks to estimate. Mineral resource estimations are not precise calculations, as they depend on the interpretation of limited information about the location, shape, and continuity of mineralization, as well as the available sampling results. The presentation of tonnage and grade figures must reflect the relative uncertainty of the estimations, rounding them to appropriate significant figures and qualifying inferred mineral resources with terms like approximately. To emphasize the imprecise nature of a mineral resource, the final result should always be referred to as an estimation rather than a calculation, according to the 2012 York Guidelines. How is an estimation performed? To explain the estimation process in simple terms, let us imagine in 3D that we are located at the center of a block, surrounded by n samples at different distances, each with a grade value analyzed in the laboratory. Since there are no samples at the centroid of the block, the grade value at these points or volume is unknown. To estimate the grade for this specific block, we assigned each surrounding sample at weight, denoted as lambda. If we choose n samples to estimate the block, we need to determine n lambdas, one for each sample. The estimated grade for the block will correspond to the weighted average of the value from the selected samples. The samples used to estimate the block are typically selected within a neighborhood around the block, defined as an ellipsoid whose radius vary according to the search configuration. We can use isotropic or anisotropic ellipsoids with axes orientated in a space based on the mineralization or spatial correlation characteristics. This means that the method chosen to estimate will determine the lambda values for each sample. For instance, if we use the arithmetic mean, all lambda values will be equal. Next, let's explore the most commonly used methods to obtain these values. The use of geostatistical tools for mineral resource estimation has become a standard practice in the mining industry. Ordinary kriging interpolation, followed by inverse distance weighting, accounts for more than 90% of grade estimation. Both methods are linear interpolation techniques. For inverse distance weighting, the lambda values depend exclusively on the distance of each sample to the block centroid. Samples closer to the block will have a higher lambda weight, while those further away will have a lower lambda weight. Ordinary kriging is a geostatistical method and it's theoretically the best linear estimator, making it the most widely used and reliable method. In this case, the lambda values depend on a spatial correlation model that defines the characteristic of the spatial continuity of the mineralization and, therefore, the geological properties of a deposit. For instance, the spatial correlation model describes spatially anisotropic in the mineralization distribution associated with structural controls. Using this model, the lambda values depend not only on the distance to the centroid, but also on how correlated the samples in the direction of the distance vector. However, there are some considerations to note about this method. While it guarantees globally unbiased estimation, this holds true for zero cutoff grades. Therefore, the estimations may not be reliable when higher cutoff grades are applied. This is due to the smoothing effect caused by the change of support, which leads to the histograms of estimated values being different from those of the data. In geostatistics, there are other methods as old as kriging theory, such as nonlinear interpolation methods. In addition to conditional simulations, two methods stand out: localized uniform conditioning and multiple indicator kriging. These methods are known to geostatisticians dealing with deposits where grade distributions are highly skewed, such as gold in orogenic, alluvial, or vein-type deposits, zinc in massive sulfide or skarn-type deposits, or for deleterious elements like arsenic, which typically yield poor results with linear estimators. Additionally, these methods have been successfully tested in the estimation of geological variables, where accurately representing data distributions in the block model is critical. The implementation of these methods might be more complex, but this is not truly a barrier, as the knowledge and software are available. Consequently, it is possible to improve estimations for making critical decisions in the mining business. In summary, grade estimations involve assigning weights to samples in the neighborhood of a block. For this, we use linear interpolation methods such as inverse distance weighting and ordinary kriging, as well as nonlinear interpolation methods like LUC and MIK. Finally, we encourage further training, breaking the paradigm of relying on a specific software and improving the understanding of the benefits of using these tools to optimize estimations and enhance the predictability of models. In the next chapter, we will delve into the final topic of this season, one of that interests me greatly: reconciliation. I invite you to stay tuned for our next chapter, where we will continue discussing and learning more about the geo-mining metallurgical business in Chile and the world.